Welcome, everyone. Thank you for joining us today for our Solar HALE webinar. My name is Olivia Matipier, and I'm a marketing analyst at Alta Devices. Alta Devices designs and manufactures thin, flexible, and high-efficiency solar material designed to empower autonomy in unmanned systems. Today, we're discussing selecting solar for HALE. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box in your Zoom control panel. We will reserve time for questions at the end. This webinar will also be available to download on our website soon afterwards. Before turning things over to our presenter, I'll walk you through today's agenda. We'll start off with an introduction to HALE aircraft, why solar is such a good source of power for them, and how to evaluate the different solar materials available today. Then we'll dive into the Alta solar technology solution and how to optimize the power available on HALEs using Alta solar cells. Now, without further ado, I'll turn things over to our presenter today. Speaking today is Ian Murray, Technical Marketing Engineer at Alta. Ian has been at Alta for 2 years. Since joining, he is focused on the integration, implementation, and development of solar for UAVs, small satellites, and high-altitude, long-endurance aircraft.
Hi, thank you, Olivia. Great to be here today. So just to go ahead and get started, here at Alta, we produce the world's most efficient, thin, and flexible solar technology designed to power autonomous systems. We currently hold the world record for single junction cell efficiency at 28.9%. Our solar technology enables vehicles to recharge while in motion and extend endurance, yet has minimal impact on aerodynamics and design. Our primary markets are UAVs, automotive, spacecraft, and sensors. Our solar is an enabler for these systems. Currently, we manufacture all of our solar cells at our headquarters in Sunnyvale, California, but we're also in the process of scaling up and expanding globally. So today's focus is on HALE aircraft, and HALE refers to high altitude, long endurance, or also high altitude pseudo-satellites or HAPS. Both of these types of UAVs or unmanned aerial vehicles are actually being developed for 2 end uses. The first is telecommunication services for markets across the globe, and the second is for surveillance. So using traditional power sources, HALE aircraft can only operate for a few days. For longer missions of multiple weeks or even months, solar cells are really the only viable power source. So as the name implies, HALE aircraft fly at very high operating altitudes, typically about 20 to 25 kilometers, which is well above commercial air traffic, which is typically 10 to 15 kilometers. And HALE also fly in an area of very little wind. So the challenge that presents itself at high altitude is low air density, requiring low aircraft weight with a relatively higher power output. Considering you can't economically refuel or plug in an aircraft mid-flight, the solar presents itself as a front runner in power sources for these aircraft. Solar is readily available and can be used to charge batteries during the day and then used to power propulsion at night. The winter season is more challenging with low solar energy available over a 24-hour period. So using a higher efficiency solar technology can help address this issue. A good example of a solar HALE aircraft is the NASA Helios, built by the California-based company AeroVironment with the assistance of NASA. So its maiden voyage was in September of 1999. It is extremely wide with a wingspan of over 80 meters, larger than a Boeing 747. The Helios was a flying wing design. At the time, it set a record for flight altitude of 29,524 meters. This record has only been bested by rockets or high-powered jet aircraft. The NASA Helios was covered with 62,120 crystalline silicon solar cells. So these cells, they had efficiency of around 19%. If the NASA Helios had been covered with gallium arsenide solar instead that Alta uses today, it would have resulted in a power improvement of about 30%. It would have also resulted in a major reduction in weight. Another example of a solar HALE aircraft that's been in the news recently is the Airbus Zephyr S HAPS. On August 8th of this year, the Zephyr broke the record for the longest flight by an unmanned aircraft without refueling. It was in the air for a total of 25 days, 23 hours, and 57 minutes. The Zephyr has a 25-meter wingspan and weighs less than 75 kilograms. Airbus recently announced the opening of a serial production facility for the Zephyr HALE aircraft in Farnborough, England. A good question asked when considering solar for HALE aircraft is, how do you evaluate solar performance? The dominant performance metric is efficiency. There are other metrics relevant to HALE market and environment. These include the power to weight, the power to area ratio, the packing factor, the ease of integration of the aircraft design, how durable the material is. So if we take a look at the relationship between power, weight, and area, in order for an aircraft to stay aloft at high altitudes for long periods of time, weight needs to be minimized. Solar panels are usually integrated into the wings, so the weight of the solar leads to increased aircraft weight. It's important to remember that weight includes the solar cell weight, the protective packaging needed, any additional structural support for the cells to survive in environmental conditions at the 20 to 25 kilometers of altitude. So the lighter the solar, the better. Minimizing the area needed for the solar is another important consideration, is usually measured in power per unit area. So power to area should be computed at the array level in addition to the cell level. The crucial variable that affects how much power you can have per area is the packing factor, or the ability to pack in more solar area to a given area. A solar cell manufacturer able to provide customized sizes and shapes for solar cells and solar assemblies to ensure maximum utilization of available area is crucial to maximizing power. So you can see the NASA Helios did a really good job of this by using all the available wing space, even on the curved surfaces. So if we compare how Alta Devices technology does compared to other types of solar using metrics of power to weight and power to area, you can see both the Alta single and dual junction cells are very high performance. Ideally, the solar you choose to add to a HALE aircraft doesn't impose any constraints to the aircraft design or how it's manufactured. So thin and flexible solar technologies are easier to integrate because they're less likely to break. They're also more aerodynamic. You can take the shape of whatever satellite or aircraft is being added to. Cells can be encapsulated with a variety of plastic films and spray-on coatings. HALE aircraft fly in difficult environments. The solar cells added to these aircraft have to be able to withstand extreme temperatures, strong UV light, vibration, impact during takeoff and landing. Most importantly, the solar has to be able to last months or years on end without maintenance. So at Alta, we work with our customers to understand the environments the aircraft will be in and make sure the solar cells are tested rigorously to handle these conditions they'll face. Some of these tests include damp heat testing, accelerated environmental aging test that determines the ability of the solar panel to withstand long-term exposures to high temperature and penetration of humidity. We also put our panels through extensive shock and vibe testing as well. So before diving into Alta's specific technology, let's review the different types of solar technologies available today and suitable for aircraft integration. They can be divided into two broad categories. So you have wafer technologies. This includes materials such as crystalline silicon, traditional gallium arsenide, and thin film technologies is the other category. So that's your amorphous silicon, your copper, indium, gallium, selenide, and then finally, thin gallium arsenide. So in the category of wafer technologies, you have crystalline silicon cells that make up the bulk of existing solar cells. These are typically bulky, fragile 6-inch wafers that have a conversion efficiency of about 20%. And these wafer-based cells are generally about 0.2 millimeters thick, and they're encapsulated with very thick laminates for environmental protection. Increasing weight, maybe 3 times is what you would face otherwise if you didn't have that sort of thick protection. Crystalline solar cells are what make up the majority of solar panels you see on homes, on structures, building integrated photovoltaics, etc. So you can also make this type of solar cell using better semiconductors than silicon. For example, you can achieve much higher performance using a material called gallium arsenide. However, a wafer made from this material is prohibitively more expensive for applications other than satellites. Thin film solar cells are those that use much thinner layers of semiconductor material, usually 100 times thinner than wafer-based cells, allowing for a very significant reduction in weight. So a popular thin film technology is known as copper, indium, gallium selenide. So we just mentioned it earlier, but otherwise known as SIGs. So flexible SIG cells offer large area efficiencies up to about 13%. So a company known as Celebro, which is a sister company of Alta under the the Hanergy portfolio, holds the world record for glass plate SIG's module conversion efficiency at 18.75%. SIG cells are very sensitive to moisture and must be encapsulated in hermetically sealed packaging to last. The downside of this packaging is that it increases the product weight and reduces the ease of integration. So SIGs also yield very poor energy in high temperature and low light conditions. Another thin film technology is amorphous silicon. So amorphous silicon is lightweight, it's inexpensive, it's flexible. It's not as sensitive to moisture and air as SIGs is. However, the conversion efficiency is lower. It's about 8 to 10%. So that makes it very hard to find enough surface area on an aircraft to put enough cells to meet the power needs. So let's talk about Alta and Alta's solar solution. So thin film gallium arsenide, it's a relatively new solution to the market that exploits the fact that you don't need thick layers of gallium arsenide to absorb light. So the technology offers high conversion efficiencies of about 25 to 35%, but in a lightweight and flexible format. So these cells are not susceptible to breakage. They're not susceptible to air or moisture. They're much easier to integrate into an aircraft design than other technologies. These cells are manufactured in smaller sizes than traditional wafer-based cells, resulting in better packing density in the final product. So if we compare thin film gallium arsenide to other solar technologies available today, you can see that thin film gallium arsenide outperforms other technologies in the categories of power to weight, power to area, packing factor, durability, ease of integration with the final aircraft design. So Alta Devices Solar is well suited to meet the unique environmental conditions and mission requirements for the HALE aircraft. Now that we've covered the different types of solar that can go into a HALE, let's discuss what can affect the solar performance once it's actually on the aircraft. These factors will impact any type of solar cells at high altitude, regardless of the material. So these factors include outdoor temperature, weather, spectral irradiance, the angle of incidence of the sunlight on the solar panels. So the first factor that impacts solar performance on HALE aircraft is the weather. So again, HALE aircraft are typically in the 20 to 25 kilometer range, which is well above commercial air traffic. But temperature and winds at this altitude are fairly constant above 20 kilometers, but the air density is very low at this altitude. So this results in poor lift, poor thermal conductivity. So to compensate for this poor lift, HALE aircraft have to be extremely light. The next factor that impacts performance is the solar spectral irradiance, which encompasses wavelengths from UV to infrared. And as most HALE aircraft fly below the ozone layer and above any clouds, they benefit from unobstructive solar irradiation in addition to decreased levels of UV radiation. The spectrum's intensity varies based on the time of year, the time of day, the angle of incidence of the light to the solar panels. So when we talk about the angle of incidence, what we're referring to is the angle between the light striking the solar cell or the panel and the panel itself. So this angle is affected by the time of year, the time of day, the geographic location. It's also affected by how the aircraft is oriented. So before building a full-scale solar aircraft, it's recommended that you model the solar performance just to get a good understanding of what the solar output is going to be prior to flight. Solar efficiency is measured as the difference between the integral of the solar spectrum and the quantum efficiency of a specific solar cell. And all solar cells have properties that allow them to absorb certain portions of the light spectrum based on the various materials that are out there. Ultimately, how the spectrum changes determines the power output of the cell. So for example, the spectrum will indicate a higher irradiance in the summer than in the winter, as there are more hours of daylight. However, the spectrum will show higher irradiance on a vertical surface in the winter as the sun stays lower on the horizon for longer. And adjusting how the aircraft flies to maximize sunlight based on these different factors can optimize flight time. Performing a spectral analysis, taking into account things like temperature, angle of incidence, can be very complicated, but this is something Alta Device engineers have a lot of expertise in. So we're happy to do these calculations in support of our customer projects. So if you need help for these sorts of situations, please feel free to reach out to us about your specific project. So just to recap what we've gone over today, HALE aircraft are actively being developed into two major end uses: telecommunication services for markets across the globe and surveillance. And the world has seen a few gas-powered HALE aircraft that can fly for days at a time, but they're limited, they're heavy, they're expensive. Batteries alone cannot enable continuous operations. And the world has tried to build solar powered HALE for about 20 years now. But the solar has not been efficient or light enough to make this work until now. And thin film gallium arsenide is the only solar technology lightweight and powerful enough for HALE aircraft. So with that said, here are some additional resources if you'd like to read more in detail about our solar technology and HALE solar applications.
Thank you all for joining us today. We look forward to having you join us for future webinars. Please send any feedback or additional questions to info@altadevices.com.